So when we tried to solve a non-homogeneous second-order linear constant coefficient differential equation, we need to get the homogeneous solution first, and then we add to that homogeneous solution the particular solution. And thus far we've been finding the particular solution using unknown coefficients. Or another way of finding the particular solution is going to be variation of parameters. Now, both these methods sort of use this principle of superposition. So let's just mention what principle of superposition is. Say we've got like we have here, a linear second order non-homogeneous, and the non-homogeneous part, the target function, is the sum of two functions, g1 and g2. Both g1 and g2 are functions of time. And we know that we have a particular solution that'll hit the target g1. In other words, if I put it in the left-hand side of the equation, g1 comes out. And we've got a particular solution, y sub p2, that hits the g2 target function. So if my target function then is the sum of the two targets that I can hit, then my particular solution is just the sum of those two particular solutions. That's our principle of superposition. And I guess we were already using this with unknown coefficients, where we were making our guess, if our target function was the sum of two target functions for who, we had good guesses for each piece, and our target function was the sum of those two target functions we already knew, then our good guess with the unknown coefficients was just the sum of the two pieces. Now let's think about this variation of parameters. Now there'll be a lot of algebra in this. It's a fun lecture to teach live because the math starts out small, gets really, really huge, and then through a few simplifications collapses down. So it's kind of a fun derivation. In the end, after all of this investment that we make, we'll end up with two formulas that we can solve. There's some integration in it, and boom, we get our particular solution. So there is a lot of investment, but it ends up being worth it at the end. All right, let's take a look. So consider here I've got a homogeneous second order linear constant coefficient differential equation and a homogeneous solution for it, which is just the linear combination of two little solutions. So y1 and y2 are solutions to this homogeneous differential equation, and y1 and y2, they're functions of time, and they're independent. So we know they're independent, or if we want to prove they're independent, we can look at the Wronskian, show the Wronskian's not zero. But anyway, at this stage, we know that y1 and y2 are the solutions to the homogeneous equation. They're two little independent solutions. Now I need to get the general solution of this non-homogeneous equation. I just need to take the homogeneous plus a particular. So we need to get a particular solution to add to this homogeneous solution to get the general solution. So variation of parameters is a method to get the particular solution. Now if I take a linear combination, in other words a constant times y1 plus a constant times y2, I know if I sub that into the left-hand side of the differential equation, 0 will come out. That's the homogeneous solution. So our idea here isn't to take a constant and a constant, it's to take a function times y1 plus a function times y2. So we're not taking a linear combination where these are constants, we're taking a function v1 times y1, y1 is a little solution, and v2 times y2. And we're saying maybe we can make a particular solution out of this combination of the y1s and y2s. Now we can if we can find v1s and v2s that work. What do we mean by that work? We mean that if I sub this into the differential equation, the ay prime prime plus by prime plus cy, I get g out, that it hits the target function. That's all a particular solution is supposed to do. So if we could figure out v1 and v2 that do that, then we've got a particular solution. We add it to the homogeneous solution, that gives us a general solution, we're done. So our job is just find v1 and v2. So there's two things to find. So thinking about two things to find, two unknowns, basically I need two equations. So I'm looking for two equations that will define the V1 and the V2. So if we're subbing this in the right-hand side of this non-homogeneous differential equation, subbing this particular solution in, then I need the first derivative and I need the second derivative. So here's our proposed particular solution, v1y1 plus v2y2. The v's, both functions of time. The y's, they're functions of time. So if I'm going to differentiate this, I need to use product rule on the v1y1. So that's what I've got here. Derivative of the first, leave the second alone, plus leave the first alone, the derivative of the second. This piece is just the derivative of the v1y1. So I also need to add to it the derivative of v2y2. Now, every time I do product rule, I'm going to end up doubling the number of pieces here. There were 2 pieces here, there's 4. In the second derivative, which I also need, there's going to be 8 pieces, because the derivative of each one of these is going to have 2 pieces. Derivative of the first, leave the second alone, plus leave the first alone, the derivative of the second. Now, there can be, you're looking at this saying, well, there can be some simplifications. Why doesn't he, in the end, after he gets the second derivative, why don't I add these 2 pieces together? They're the same. That's just 2 of these. That'll simplify the equation. I don't, because I know how the algebra is going to work out down the line. I want those 2 pieces separate. But for our purposes, I've got our proposed function, its derivative, and its second derivative. I'm going to substitute it in this side of the equation, set it equal to g, and see what v1 and v2 have to be. It feels like that's the idea behind unknown coefficients, but they're not coefficients anymore, they're functions. So I guess variation of parameters could be called unknown functions, but it's not. Those parameters are functions, and we vary them, so I guess that's why they call it variation of parameters. We've got our linear second order. We're going to sub in then. I need to put in the second derivative, so it's a y prime prime plus by prime plus cy. Everything's a function of t, so I don't have to specify t's. All the y's are functions of t's, all the v's are functions of t's. Alright, so here I've got this equation. All I have to do is pick v1s and v2s, pick a v1 and a v2 that solve this equation. But we can do a little bit of simplifying. Let's move that up. Now the simplifying is, let's group on the just straight v1s here. So I've got a v1 piece here, I've got a v1 piece here, and I've got a just v1 piece here. So I'm just collecting on those v1s, and likewise I'll do collect on the v2s. So let's do that collection. So I've taken our equation, I've collected on the v1s and v2s. These are the leftover pieces here. And remember, I'm just trying to figure out any v1s and v2s that work. But notice that since y1 is a solution to the homogeneous equation, then when I sub it in the left-hand side here, I get 0 out. That's telling me that this whole bracket here is equal to 0, since y1 is a solution to the homogeneous equation. Likewise for y2. So by collecting, all of this bracket is equal to 0, this bracket is equal to 0, all these things cancel out. So it did look like it had, 20 pieces in it, but it collapses down a little bit. So let's do that. The next line. So now all I have to do is figure out v1s and v2s that solve this equation. One thing I do notice is I don't actually have any v1s or v2s left. I have v1 primes and v1 prime primes and v2 primes and v2 prime primes. But if I can figure out equations for v1 prime and v2 prime, which is actually the way we're going to go, then I can just solve for v1 prime and then integrate it. So I've still got 2 unknowns, but they're not the v1 and v2. They're now v1 prime and v2 prime, but I can deal with that. So my 2 unknowns are v1 prime and v2 prime, and I just need, how many equations for 2 unknowns? 2 equations. And they can be any equations. So here's where it seems rather arbitrary, but it worked out really nice when whole brackets of things were equal to 0 so that I could, cancel them out and make the equation simpler. So since I'm looking for two equations, I'm going to make one of the equations this bracket equals to 0. I'm saying that, so I choose this. That's going to mean that this whole thing times A is equal to G. So I'm reducing the amount of stuff I have to deal with. Now, one of the things that you're probably thinking about is, can he do that? Can you just say, let this be equal to 0? Well, if it works, yes, I can. So we got to take this, finish it all the way to the end, show that it works, and then that'll justify my creation of this equation. Remember, my only goal here is to figure out any V1 and V2, or I guess in this case V1 prime and V2 prime, that work, that solve the differential equation, that when I put in the left side of the equation, hit the target function. That's all I'm looking for. I see I get a bonus here. I get a bonus equation. If I let this equal to 0, then the derivative of both sides of this equation also has to be 0. So let's differentiate both sides of this equation. Differentiating the 0 side is easy. The derivative of 0 is 0. Differentiating this side, I got to do product rule twice. Differentiate derivative, I got to do product rule here. Derivative of the first, V1 prime prime, leave the second alone, plus leave the first alone, derivative of the second. Likewise for the derivative of the second piece. So I chose this equation, I got this equation, or this combination of stuff equal to 0 as a bonus. Now how can I use that? Well, these pieces are in here. So I've already set this bracket equal to 0. So let's take this piece. That's what I'm dealing with. Move it down here. I've already set this bracket, the B bracket, equal to 0. So that's gone. But notice, if I arrange things, I'll just take these, I'll take this piece here and move it to, take this piece, move it to the front, and I'll take this piece, move it to the front, and now, oh wait, here when I took the derivative of the V2, there should be another prime in here. So yeah, now this lines up, and this whole piece then is equal to 0. That's our bonus equation. That's why I didn't combine these two pieces together. And why didn't I? Well, because I had already seen this derivation. I know how this works, so I knew not to put those pieces together. That's another reason why I knew that I needed a prime prime here to check my derivative, because I know that this whole piece is supposed to equal to 0. So it's gone. So I think I'm done. How do I know I'm done? Well, what did I need? I needed two equations. I've got two equations. There's one equation that I just proclaimed to try it out, and here's another equation. There's two equations, two unknowns. So let's write our two equations down. We got our two equations. If we can find V1 primes and V2 primes that satisfy these two equations, and I can because it's two equations, two unknowns, then all of this will simplify down to G. So in other words, that particular solution of V1 y1 plus V2 y2 will hit the target function. So these are our two equations, two unknowns that I have to solve for V1 and V2. So here's our two equations. Two equations, two unknowns. The two unknowns are V1 prime and V2 prime. When we solve them by elimination, substitution, Kramer's rule, however you want to solve it, we get V1 prime is equal to minus G y2 over A W. What's W? The Wronskian. The Wronskian shows up when we solve this. So there's the Wronskian in the denominator. Now here's where we get to say, oh, it's a good thing that our y1 and y2 are independent solutions. That way we know the Wronskian isn't 0. So we're not dividing by 0. The y1 prime is defined. The y2 prime is defined. So in a nutshell, our particular solution is going to be v1y1 plus v2y2, where v1 and v2 are defined by these two integrals. So some instructors, or some books, some courses, you memorize these two equations and then solve them every time. This course, the one you're in, instead of memorizing two equations and solving them, since you're going to memorize stuff anyway, let's just memorize the pre-solved formulas. There is a pattern. The v1 has a y2 on top, the v2 has a y1 on top. They're both g on the top and aw on the bottom. The w is the Wronskian. We know that's not 0. We do that integration. So to solve for the particular solution, which is what variation of parameters is supposed to do, we need the 6 ingredients. We need G, A, W, or G, A, the y1 and y2 little solutions and their derivatives. We pop them into these formula, do the integrations, put them in the right part for the particular solution, and we're done. Let's do an example. This example, we just want to find the particular solution to y prime prime minus 5y prime plus 6y is equal to e to the t. Now, if this wasn't the video on variation of parameters, I would just do this by unknown coefficients. Our guess would be, our target function is e to the t, so our guess for unknown coefficients would be our particular solution is a, some constant, e to the t. The derivative of a e to the t is a e to the t. All the derivatives are a e to the t. So we'll have a e to the t minus 5 a e to the t plus 6 a e to the t. Clean that up, I get 2a e to the t is equal to e to the t. The a must be a half. There's our solution by unknown coefficients. Again, an easy way to get the particular solution when it works. But let's test our variation of parameters method on a question whose answer we already know. So we know that our method's working. There's 6 ingredients that we need. We need the y1 and y2. Oh, how do we get those? Those are the little solutions to the homogeneous equation. So I got to go back and think about the auxiliary equation, which would be lambda squared minus 5 lambda plus 6 equals 0. The roots of that, the eigenvalues, would be 2 and 3. So I get real and different roots. I have my two little solutions, e to the 2t and e to the 3t. The homogeneous solution will be a linear combination of those two solutions. But I need the y1 and y2 for our variation of parameters. I need the derivatives of those functions. The a is the coefficient in front of the y prime prime, 1 in this case, and the g is the target function, the e to the t. So here I've got all 6 pieces that I need to put into the formula that we developed. Let's calculate the Wronskian then. The Wronskian is going to be y2 times y1 times y2 prime minus y1 prime y2. So our Wronskian, not 0, we knew that, is e to the 5t. That'll go in the denominator of each one of these two pieces. So let's set up our functions here. Our y2 is e to the 3t, and our y1 is e to the 2t. So now we put in all the pieces. When we're integrating here, this integration simplifies to be, well, what are we integrating? We're integrating minus, you got a 4t on the top, e to the 4t, e to the 5t, so it just integrates to be e to the minus t. And we integrate that, we get e to the minus t. Our second integration then for our v2. This will be e to the 3t on top divided by e to the 5t. So we're integrating e to the minus 2t, which integrates to be minus a half e to the minus 2t. Oh, what about the plus c's? Well, long story short is you don't need the plus c's. What if you put them in anyway? Or why don't we need the plus c's? If you do put them in anyway, then they'll cancel out, or they'll be absorbed as part of the homogeneous solution. Because if I have a constant included for the v1 and I distribute the y1 across that, I'll get y1 times this, the v1 piece that I really needed, plus a constant times v1, which will just be absorbed into the homogeneous solution. Long story short, as I said, you don't need the plus c's in this case. So now I've got these constants. Now I've got the v1 and v2. They're not constants. They're functions. I'm looking for the particular solution. The particular solution is v1 y1 plus v2 y2. So I need to put those v1 y1 plus v2 y2. And when I simplify that, here's e to the t minus a half e to the t, I get what I got up here, a half e to the t, which of course I expected to get that. So there's my particular solution obtained through variation of parameters. So I guess now you're probably saying, why do I need to know two methods then? If the one easy method, the first method that we learned, the unknown coefficients, does everything. Well, it doesn't. So here's a question where I need to find the particular solution to this, but I don't have a good guess for this e to the 2t divided by t as a target function. I can't just use a e to the 2t. I'm never going to get this divided by t. If I think about it for a bit, I can't think of a good unknown coefficients. So I think I'm stuck with, or I'll try, no, I'm stuck with variation of parameters. So let's find the particular solution by variation of parameters. I need the six things then. I need the a, that's one. I need the g, we got that. I need the y1 and the y2. Oh, to get the y1 and the y2, I'm going to have the auxiliary equation. The auxiliary equation, which factors, and I get eigenvalues of 2 and 2. I've got repeated eigenvalues, real and repeated eigenvalues. So I know my little solutions are. They have to be independent. So y1 is going to be the e to the 2t, and the y2 is going to be t e to the 2t. So I need those two pieces, and I need their derivatives. I've got the derivatives. I know that a is equal to 1 and g is equal to this e to the 2t divided by t. Let's use the variation of parameters method. So what do I need? Let's get the Wronskian first. So y1. So I've got the Wronskian. When I simplify it, I get e to the 4t, again not equal to 0, but we've got the piece that goes under here. So let's set these up. The a is 1 and the Wronskian is the e to the 4t. So now I've subbed in for the Wronskian, the a, 1, the g. I just need to put in the y2. All I have to do is simplify and integrate. But let's take a look. On the top, the t's cancel, and I get an e to the 4t divided by e to the 4t, this with a minus sign. The v1 just integrates to be, or simplifies to be integrate minus 1 with respect to t, so that's just minus t. The v2, okay, the e to the 4t's cancel top and bottom, but, oh wait, no minus sign in the second piece, but I end up integrating 1 over t dt. which is ln of absolute value t. So now I've got the v1 and v2, so my particular solution is going to be v1 y1 plus v2 y2. There's my particular solution. I can add it to the homogeneous solution. Let's do that. Let's get the general solution because there's a point I want to make here. If I add it to the general, or add it to the homogeneous solution, which would be C1 y1 plus C2 y2, which would be t, e to the 2t, plus the particular solution. There's my answer. Homogeneous solution plus the particular solution. Now, maybe I turn to the back of the book and I don't see that because an equivalent is I could absorb this piece into this constant. So these pieces might be written as one term, which would be a constant times t e to the 2t. But the method produced this extra piece. Both answers are correct. And let's go back to this question. I could never have solved this with unknown coefficients, so I need both methods. Now, for those of you thinking like, all right, unknown coefficients does stuff, but variation of parameters does stuff unknown coefficients doesn't do, so, but it does unknown coefficients solvable equations too, so why don't I just learn one method and that's it? That's a bad strategy. Unknown coefficients, when it works, is easy and fast and doesn't produce any integration. So your best strategy is to know both methods. Let's do one more example. So now look at this. I would actually, if it wasn't the variation of parameters video, I would do this with unknown coefficients as well. The good guess would be a sine t plus a cos t for your variation, or for your unknown coefficients particular solution. But let's do it with the variation of parameters. When I look at this also, I see that the homogeneous part, that's simple harmonic motion. So simple harmonic motion, I can see that the eigenvalues are going to be plus or minus I, because the auxiliary equation is lambda squared plus 1. So my little solutions are going to be y1 equals sine t and y2 is equal to cos t for our little solutions. Oh, wait a minute. I go back and think about, I was going to do unknown coefficients with a sine t and b cos t, but that would be the homogeneous equation. So I guess what I would have to do is throw a t in front of everything. If I was going to do this unknown coefficient, I would want to do it as a t sine t plus b t cos t. And that would work. But let's do our variation of parameters. We need the derivatives, y1 prime and y2 prime. When I take the derivatives, let's just do the Wronskian right now. It's going to be, the Wronskian is going to be minus 1, not 0. The a is 1, the g is sine t, so let's get our pieces that we need here. Our Wronskian we already got is minus 1. So we're going to be integrating sine times cos, and for the v2 we're going to be integrating sine squared. So now all we have to do, well, there's some trig integration techniques. That minus 1 is going to cancel with that minus 1 on the bottom. I've got a sine and a cos. I can do this by substitution, or think of this as half of sine 2x formula. Regardless, we have ways of integrating this. Our sine squared, I would write that with our double angle formula and integrate. We've got our v1 and v2. So our particular solution then is going to be v1 times y1 plus v2 times y2. Things to note. The frequency of the homogeneous solution must be, oh, I've got my initial conditions here too. Let's figure out our initial conditions then. The initial conditions, I need the general solution to sub that in. So our general solution is going to be a homogeneous solution plus the particular solution. It's only now at the end that I use the initial conditions to figure out the constants A and B, C1 and C2. I think I call those K1 and K2. They're two constants. Let's invoke when t is equal to 0, y is equal to 0. So that means 0 equals, sine of 0 is 0, cos of 0 is 1, sine of 0, that's all 0. So b is equal to 0. That means our general solution must be of this form. Now I need to take the derivative of it so I can invoke the second condition here, that the y prime naught is equal to 0. Now that slope is equal to 0 when t is equal to 0, so cos of 0 is 1, cos of 0 is 1, cos of 0 is 1, so this is going to be a half minus a half, 0, this whole piece disappears. Cos of 0 is 1, cos of 0 is 1, so this whole piece becomes minus a quarter. Sine of 0 is 0, sine of 0 is 0, so I get a is equal to a quarter. So now, at the very end, we can write out what our solution is. There's our solution. The thing I was going to point out up here at the top, before I go, could we even see that? There's our solution. Here's our solution, is that let's look at our question. In our question, we had simple harmonic motion as the homogeneous part with a frequency of 2 pi. And our forcing function, if I'm thinking about this as like a spring, our forcing function has the same frequency. So we hit this resonant frequency. We start at 0 with the slope of 0. It's at the equilibrium and it's not moving, and yet, here's our answer. When t goes to infinity, this waves up and down, this waves up and down. But this part goes to infinity times a cos, so our answer starts to, it oscillates off to infinity. It oscillates off to be unbounded. And that makes me want to think about then, what is, so this is our final point here. We're talking about the limit as t goes to infinity of the general solution. Can we make any proclamations about that? Well, we do know that in general, when I take the limit as t goes to infinity of the general solution, that's just the limit as t goes to infinity of the homogeneous solution plus whatever the limit as the particular solution goes to 0. So let's just put that in there, the particular solution. What the point I'm trying to make here is that if the eigenvalues of the equation both have negative real part, then this piece, the homogeneous solution as t goes to infinity, is equal to 0, and so eventually the solution just approaches that of the particular solution. So the homogeneous solution dies out and the particular solution takes over, which means that if the eigenvalues are both negative real part, it doesn't make any difference what the initial conditions are, because the initial conditions show up in the c's, in the constants, and those constants are in the homogeneous part, and that homogeneous part goes to 0, leaving you only with the particular solution. So questions that ask things like, what does the solution eventually get to become? The answer is the particular solution, if the eigenvalues have negative real part, both of them. If one of them has positive real part, or both of them has positive real part, then the answer is infinity because the homogeneous solution shoots off unbounded, and I guess it doesn't make any difference what the particular solution is then, in general. Now it's all practice. It'll be assumed that you have those V1 and V2 formula. It'll be assumed that you have all those formula, the nutshell piece. It's assumed that you have all this memorized by now.